All right. So part B is just, stop talking here, folks. It's just drawing a picture is all we're doing here for this. We're going to use our answers from part A to draw our picture. So I'm going to just cheap out and use some technology here to make this a little bit easier. So y equals e to the x. And then I want my grid range just going from 0 to point, I don't know, we'll do 0.5. And then we'll go from 0 to, I don't know, like 1.6 or something, I think. Should cover everything. So this is, purple is e to the x. Our initial condition was the 0.01. And then our first equation, our first approximation was the point, let's see real quick. For 0.04, we just went straight to what do we get? We got 1.4, right? Oops. So I would just draw the line through those.
I didn't really understand what's asking.
Yeah, so just...
And then are you just repeating that?
And then we're doing it for the next one, except here we have 2 points to build out our line, right?
Okay.
So we had 0.2 and 1.2. And then we had 0.4 and 1.44. So there we're getting a little bit closer, right? And then the third one, we had 0.1 and then 1.21. Yep. And then we had, oh, I'm sorry, not that. I was, sorry, reading the wrong thing. It was 1.11. And then we had 0.2, 1.21. And we had 0.3, 1.331. And then we had 0.4, 1.4641. So I'd connect those points. And I'm noticing all of these were an underestimate, right? Because I can see they're all below the curve. But as I'm getting, that step is getting smaller, the gap between my final estimate and the curve is decreasing each time, right? Is that cool with what? So I would use some kind of like something like this and then just connect some dots. I'm not going to try to draw that by hand. It's awful aggravating to try to draw that much accuracy. But like use Graphmatica or Desmos or, you know, your calculator or whatever. It's just a sketch or whatever. It's fine. Cool? Okay. Yeah, no problem. Those are awesome ones, right? Where it's just like, oh, it's all we're doing is plotting some points and drawing a picture. Yeah, that's all you need to do. Who's next? Happy to do more if you guys have some more. Okay. Paul, is that? No? You good?
Sorry, Sergio's.
That's okay.
Wow.
All right. In general, I think that like 9.1 and 9.2 should have been pretty straightforward. Oh no. Well, that's going to be a hassle. They never moved those over, huh? Easy enough. All right. So section 9.3, we're going to be talking about a technique to solve these differential equations algebraically. So in 9.1, we talked about how you can confirm whether something's a solution to a differential equation just by taking its derivative and plugging it into the differential equation, seeing if it matches out. In 9.2, we saw, okay, well, we can take our differential equation, create a slope field for this, and then sketch in a possible solution if we have an initial condition, or we can draw infinitely many possible solutions if we don't have an initial condition. In 9.3, we're going to start looking at algebraic methods to solve these differential equations. So these methods tend to be some of the more valuable to us because, well, in 9.1, you need to know the answer if you want to check it and confirm it. Well, how do you get the answer? 9.2, we can get an answer, but we get a graph out of an answer, not in like a equation form. And creating a slope field is rather tedious. In 9.3, we're just going to look at how to do this algebraically, symbolically, which is going to be kind of the easiest way of doing this for us. So we're going to start with doing this for separable differential equations. So when we call this thing a separable equation, it means that our derivative can be written as a factor or as a product of a function of x times a function of y. So my derivative dy dx equals f of x times g of y. Right? It just has to be written as the product of two functions, or be able to be written as the product of two functions. Right? It might not be written exactly that way. You might have to do some factoring or something to get it the way you need it, but you can do it. What we would do then is we would separate and get the y's on one side and the x's on the other. So we divide both sides by g of y and multiply both sides by dx, giving us 1 over gy dy equals f of x dx. And then we can integrate both sides because the variables are separate. Integration will work as it has in any of the previous sections from there. So we're just going to run through some examples here now of doing this. So part A, again, it says to solve the differential equation. So my goal here is going to be to separate these. So I want to get the y's on one side. So I'm going to multiply both sides by y squared. and multiply both sides by dx. Everybody okay with how I got to here? Now that the y's are on one side and the x is on the other, I can integrate both sides, and it becomes an easy integral to do. So what's the antiderivative for y cubed, or for y squared? Over 3. And the antiderivative for x squared? X cubed over 3, right? And then what else should we write here? Yeah, these were indefinite integrals, so they both need like a plus c at the end. And technically speaking, these are different c's, so I'm going to add a subscript. They don't necessarily have to be the same constant. They could be, but they don't have to be. And then usually we would move the constant all to one side. So if I subtract c1 from both sides, c1 or c2 minus c1, I'm just going to call that the constant c. Everybody's okay with that? Since a constant minus a constant, so just another constant. What's the takeaway here with the constants? If I integrate both sides, I just need to tack a plus c on one side or the other. It doesn't matter which side you put it on. You can just put one c. You don't need to do two separates like we did there earlier. It's fine to do it that way, but save yourself some time, right? Now, typically we want to write our solution as a y equals when possible. Certainly in this case that would be possible. So to get the y by itself, I'd multiply both sides by 3. 3 times a constant is still just a constant, so I'm just going to leave it as c. Everybody's okay with that? And then we'll cube root both sides. And this will probably be the answer, or the form of the answer in the back of the book would be something like that. But that was pretty easy, right? The calculus there wasn't difficult. What's the worst case scenario for something like this? You might run into one side being like a integration by parts problem or something. Like that's kind of as nasty as it would get, is you run into something like that, which is not that big of a deal because we've practiced it a little bit. Part B says then to find the solution of this equation that satisfies the initial condition y of 0 equals 2. So we have this, right? What I want to do is solve for c when y is 2 and x is 0. Yes, sir?
So it doesn't make a difference if it's like 3c or 4c.
Correct. Yep. Because a constant times a constant is just a constant, right? We're just going to call it c, and whatever you do to it, it just stays c. So to get the c by itself, we'll cube both sides. And we get that 8 is equal to c. So my final solution then is y equals the cube root of x cubed plus 8. That's all she wrote. Not a big deal, right? Again, the only way this is going to get harder is if the algebra to separate gets hard, or if you run into, the integral that you need to take is like an integration by parts kind of problem or something, right? That's the only way this is going to get hard. The idea is pretty straightforward. So let's go ahead and look at the next example. So here we have dy dx equals 6x squared over 2y plus cosine y. So again, I'm going to multiply both sides by the stuff with the y's, 2y cosine y. And then multiply both sides by dx. That'll separate my variables to get y, all my y's on one side and all my x's on the other. Everybody happy there? Now I'm in a place where I can just integrate both sides. The left-hand side, because these are two things are being added, I can just do their antiderivative separately, right? So the antiderivative of 2y is y squared. The antiderivative of cosine is sine, because if we take the derivative of sine, we should just get cosine, right? So the antiderivative should just backwards. And then the antiderivative of 6x is
6x squared.
over 2.
6x should be 6x squared.
Oh, thank you. The antiderivative of 6x squared is 6x cubed over 3, or 2x cubed. Yeah. And I'll put the plus c over with the x's, since eventually I would hope I can get the y by itself. Although if I look at this problem, is that going to be possible? Not with a polynomial plus a trig thing. There's going to be no way to separate that y out of there. This is as good as we got. So just as an aside, what is that thing going to look like? Just so we can kind of see here. So y squared plus sine y equals 2x cubed. And then, right, we can have some constants tacked on to the end there. So like there's a bunch of different solutions of what this could look like. Everybody's okay with what we did?
Why do you have to stop there?
Well, because it's not possible to separate the y, or to get the y in one place, because I have one of the y's a polynomial and the other's inside of that sign. So there's not going to be a way for me to like get those y's into one place, right? It just, we're done. And we weren't given an initial condition, so we can't solve for C. So there's really nothing else to do here.
Okay, thank you.
Yeah, no problem. Those are great questions, right? Just like knowing when you're done, you know, that saves a lot of time rather than having to sit there and look and look and look. Okay. All right. So next one, we have y prime is equal to x squared y. Here I would do one thing before I get started. I would rewrite y prime as dy dx. Important we do that since we're going to be separating variables. So I'll divide both sides by y and then multiply both sides by dx. Everybody feel so far so good? integrate both sides. What's the antiderivative of 1 over y? Close. Natural log of absolute value y. I get you guys with that all the time. And the antiderivative of x squared is x cubed over 3. Okay. And I'll put the plus c over here. Okay, this one should be separable because the y is just in one place. I have just one y, so I should be able to get that by itself. What's the first thing I need to cancel out to get the y by itself? The natural log. How do I cancel the natural log? Exponent base e. Yeah, so we'll do that. Oops. Everybody happy there? Now what do I have to get rid of? Absolute value. How do I do that? Well, what if I have just like the absolute value of y is equal to 2? What are my solutions for y? Negative 2 and 2. So I'm just going to do here, I'm just going to say y is going to equal plus or minus. Yeah. Everybody feel okay there? Now, this is not going to be the way that they would write the answer in the back of the book or the way they'd write the answer in like a multiple choice. So let's show you what else we can do here. When I have addition going on in the exponent, that's the same as, yeah, multiplication, right? E to the c, if c is a constant, is itself just a constant, right? So this would likely be the way that would be written on a multiple choice or in the back of the book if you tried to look this one up. Do you like it when I use C's all the time? Should I use a different letter here? Use K or something for constant? Okay, doesn't really matter to me. Like, just keep calling them C's. They're all constants. I don't mind. It's done pretty universally like that, but if it weirds you out a little bit, put a subscript on it, put a star on it, whatever it helps. If you need to do that, or use a different letter or whatever, A, B, C, whatever. Okay. That's about it for this section. So in that section, I'm going to ask you to do 1 through 17 odds and then 19 to 24. Everybody's okay there? We're also going to do a little bit of 7-4. I'm not going to do all of 7-4. And to be clear, 7-4 is not an A-B topic, but it's something you would very standardly do in your first, like a first or second year calculus course. So we're going to do that as well. We're not going to do all of the iterations here in 7-4 because there's like, this just, bless you, because this thing just kind of keeps going on and on and on forever. Not really forever, but like it goes on for a ways and gets annoyingly complicated. Paul?
Why don't we do the calc BC here? Because I feel like we learn like can we just like not cut out for it?
Well,
Like you
part of it is the date in which the course ends. Makes it rough to try to, because there's, like, we do some of these BC topics, sure, but there's like 2 chapters of BC things that we don't touch. Like, we don't do anything with like Taylor series, which is not easy, and we don't do anything with like parametric or polar calculus, which is not bad, considering what you do in your pre-calc class. That would not be a problem. The Taylor and Maclaurin series stuff is it's kind of it's pretty hard. I think it's the hardest thing in BC. But that's the biggest issue. And some schools do like BC period, like you do BC in 1 year. Other schools will do AB as a year and then BC as a year, where the first semester of BC is like, we're going to do AB light, like go through and hit some of the, trickier topics, just do like foundational review, like add in maybe the couple of things that we've done that you didn't do during AB. And then the second half of the course is just like these 2 chapters of things that you don't touch in AB and are kind of unrelated to the things you do in AB.
That makes sense.
Sergio?
I did part of it because we have like IBHL math. That kind of like.
Well, the likely candidate would be someone that would be ready to take calculus as a junior. Most schools that do BC do it as like an AB and then a BC. But it just kind of depends. Part of it is the size of the school. Like, there's not a lot of students that are ready to do that as 18-year-olds. And if you have a small school, you just have that many fewer of those kinds of kids. There's only so many places to put them if you have this class and an HL class. There's only so many places you can go. But imagine having to do this class and do it maybe almost twice as fast.
Yeah.
It would be rough, right? That's what we'd be trying to do, is you'd have to find room for 2 more chapters plus some hard stuff that we could. I don't know if you'd like it anymore. All right. So let's talk about this section 7.4 here a little bit. So in the last chapter, we talked about some of the techniques that we had for integrating a rational function, right? And we saw there were a couple of situations that we could make things kind of work. So we saw when we had a situation where the degree of the numerator was 1 more than the degree of the denominator. Or I should say equal. You just did the polynomial division, and then whatever fell out of it was going to be fine. More often than not, you could get away with just doing that. We saw that, okay, if I have a 1, or if I have a constant in the numerator and a quadratic in the denominator, I might be able to like cram this into like a tan inverse or a sine inverse with a u sub. But what about just like any rational function in general? Like something like x plus 5 over x squared plus x minus 2. Well, I know that at some point to get this, I would have had to add or subtract 2 things that looked like this, right? And each of these is easy to integrate just using the log or natural log antiderivative with a u sub, but they're easy integrals to do. The question is, okay, if I can find a way to go backwards and break that up into those simpler rational functions, I would then be able to integrate this more complicated thing quite easily, right? So that method of taking a rational function and breaking it up into the sum or difference of simpler rational functions is called partial fraction decomposition. So let's go ahead and show you guys how to do that. So let's say we want to do the partial fraction decomposition for something like x plus 5 over x squared minus 2. Now I've made a point of showing you the answer, like I know this is what we're going to be getting. But let's kind of work through the process of how we'd go about doing that. So I would start by factoring the denominator. So x squared plus x minus 2. Well, how does that factor? It's going to be x plus 2 times x minus 1. Everybody okay with that? So this x plus 2 times x minus 1 is the common denominator for some addition or subtraction problem. So I know if I was going to be adding two things, the denominators of those, one of them has to be x plus 2, the other denominator has to be x minus 1. When I add them together, I'll get the common denominator in my desired, or the desired common denominator, right? Bless you. Now, I don't know what those numerators are, so I'm going to just write them as a variable, a and b. I'm going to now treat this like an equation. So I'm going to multiply both sides by x plus 2 times x minus 1, which will, in part, clear the fractions out of there. So when I multiply x plus 5 over x plus 2 times x minus 1 by x plus 2 times x minus 1, I just get x plus 5.
What did you do? You multiply that denominator over?
I multiplied both sides by that common denominator, just like we would do when we clear fractions to solve a rational equation. When I multiply x plus 2 times x minus 1 to a over x plus 2, I end up with a times x minus 1. And when I do the same thing to b over x minus 1, I get b times x plus 2. Is everybody okay with how I've gotten to this equation? Okay. I'm going to go ahead and distribute my a and my b through now. Everybody's happy with that. I'm going to use that equation now to form a system of two equations. So I know that ax plus bx has to give me 1x.
Why would we have like 2b?
Oh, thank you. And I know that negative a plus 2b has to give me 5. I now can solve that system to find the values for a and b. What's going to be the easiest way to solve that system? Okay, even easier than that. That's a good method. Elimination. Easier than that even. Put it into your calculator and use the row reduced echelon form with a matrix, right? Like this one, that would elimination is probably just as easy as doing this, but if this becomes a 3 or 4 variable system, yuckarooskies, I am glad to have this as an option. Do you guys all remember doing this from your previous classes?
Yeah.
Okay. So I'm not going to spend a bunch of time walking through what to do here since we remember doing this. If you don't, speak up and we'd happily do it again.
Yeah, do you mind just walking through the setup?
Sure. So let me just type this in here and spit out the answer, and I'll come back and do that. So A is -3 and B is 4. That doesn't seem right. Did I mistype something there? Yeah, I did something. Missed my negative sign. Okay, so look, what I did is I started by setting up a matrix. So I pressed second and then the X to the -1 button. Went to the edit command to edit my matrix. I picked matrix A. I know that the first number here is the number of rows and the second number is the number of columns. I have 2 equations, but I have A's, B's, and answers, so that's 2 rows and 3 columns. I'm just going to type in the coefficients then as they appear in the matrix. The equal sign always has to be on the right to do this. So I just did 1, 1, 1, -1, 2, 5. I'll exit out of here. I'm going to go into the matrix menu now, go to the Math tab, scroll to the bottom till I find the RREF command, and I'll do that on matrix A. And the last column gives me my solutions. So it says that I put my A's in column 1, so A is -1. I put my B's in column 2, so B is 2. So that tells me then my composition. If I go back here, I have -1 over x plus 2 plus 2 over x minus 1. So that's my partial fraction decomposition. Okay. Let's do one again. Let's do this one. Actually, let's just talk about this for a second. If I were to do this, do I need to do a partial fraction decomposition for this? No, why not? Well, the degree of the numerator is bigger than the degree of the denominator, right? So I know that I can just use polynomial division, knock that out into a polynomial plus constant over x minus 1. That's easy to integrate. So you're dead on there. If I look at example 2, though, I can't do the same thing here because the degree of the numerator is less than the degree of the denominator. So I know there's no polynomial division to be had. This one I have to do a partial fraction decomposition to be able to do this. So I'm going to begin by factoring the denominator. What do you notice that I can do there? Great. Just okay. And then remember to factor one of these where the leading coefficient is not 1. That's a little bit more time consuming, right?
Yeah.
I would just guess and check this bad boy, because I know that if the constant has to be -2, one of these things has to be -2 and the other has to be +1. And one of them has to be x and the other has to be 2x, so I just have to get them in the right place. So I know that the, So let's see, I need the 2x has to multiply the 2. That'll give me a 4x, and then the x times the -1 will give me a -1x, and that'll give me the 3x in the middle, right? So I just kind of guessed and checked it. You could do it the long way if you wanted to. Boo. I'm going to just guess and check it because the numbers are really easy. Okay. So now I'm going to set up my partial fraction decomposition. What are the fractions I'm going to need here? A over, nope, x, great. And then b over 2x minus 1. And then c over x plus 2. So far, so good? Okay. What am I going to multiply both sides of this equation by now? I'm just going to do it this way. That common denominator. So when I multiply to here, I just get the numerator. When we multiply to here, what do I get? A times 2x minus 1 times x plus 2. And my pen just stopped working for some reason. Apparently OneNote just froze on me. That's lovely, OneNote. My computer's been misbehaving all morning. There we go. Oh, maybe now are we working? Oh boy. All right, well, be okay for now. And the next one, I'm going to have b times x plus 2. And then I'm going to have plus c times x times 2x minus 1. Everybody okay so far? Okay. So that's going to give me 2ax squared. And then I have 2x minus x, so that's just going to be an ax, and then minus 2a, and plus bx squared plus 2bx plus 2cx squared minus cx. So how many equations am I going to have in my system? 3. I'm going to have one for the coefficient on my x squareds. So I have 2a plus b plus 2c has to equal 1. My next equation is going to be the coefficient on my x's. So I have 2a, I'm sorry, just a, plus 2b. Oh, OneNote, why are we doing this? Oh, maybe it's not OneNote, maybe it's my whole machine right now. Okay, did that just, did we get it? Did it do something? Oh, good. Plus 2b minus c equals 2. And then my last equation is for the constants. So -1 equals -2a. That's it. So we're going to go ahead and set up a new matrix. This one's going to be a 3 by 4. Got that in. So there I get, oh brother, is that the right answers? I have to go look here real quick. Let's see. Yeah, that's not right. A should be 1/2, which I got, but the B and the C are wrong. What did I type in wrong?
It's supposed to be 1/2 and 1/5 and negative.
Yes, yes.
It's both the A in the second row is supposed to be 3A.
3A here?
Yeah.
Oh, where did I miss my 3A at? Here, hold on one second. Okay. So, oh, sure, 2A and then plus X. Okay. Thanks, Justin. Somebody's paying attention. I appreciate that. It's a good poll. There you go. Oh my God. Yeah. Okay. So, what does that give us now? That's going to allow us to do this integral Everybody okay there? So I can just kind of distribute that integral through. So this first integral, what's the antiderivative of 1 over x? Natural log absolute value x. Here for this one, I have to do a u sub. So I'm going to just kind of write that down, but do the rest of it in my head. And here, this is like the easiest like u sub problem of all time, but technically still a u sub. And then I just need my plus c at the end. So again, the partial fraction decomposition was the lengthy part. That was the time-consuming piece. But it gets us to a place where the integral is pretty easy, right? The actual process of doing the integration was definitely something we had all the tools to handle. It was just finding a way to break up that fraction into pieces we can handle. All right. I'm going to do one more example and get on our merry way. Sound good? So we're going to talk about the case where we have repeated linear factors. So notice here, what do you notice? Well, you should notice that the degree of the numerator is greater than the degree of the denominator, right? So we can do polynomial division on this. I'm not going to write that out. I'm just going to just say this and then write the answer. Is that okay with you guys? Okay. Again, that's something we should be comfortable doing. If you're not, come back and see me and we can certainly go over it again. So for the time being, I'm going to forget about the x plus 1. That's easy to integrate. We'll just have to remember to put it back in when we get to the integration step. What I need to worry about, though, is doing the partial fraction decomposition for this guy. So how am I going to start? I got to factor that polynomial. How does that factor? How do you factor something that looks like that? Oh, guys, it's algebra 2.
That's why I've been trying to learn.
Yeah, we use factoring by grouping. So we can take out an x squared from the first group and a -1 from the second group. So that can become x squared minus 1 times x minus 1. When there's an even number of terms, factor by grouping is a reasonable approach. And then the x squared minus 1, I notice, is a difference of 2 squares, right? That's x minus 1 times x plus 1. So I have 2x minus 1s in the denominator, 1x plus 1. Is everybody okay there?
Well, then what happened to the x squared?
Well, that factor to x minus 1 times x plus 1, right? That's just a difference of 2 squares.
Then what happens?
Well,
Then the x minus 1 squared.
X minus 1 times x minus 1 is x minus 1 squared. And then I just have the x plus 1. Right? These two went together. And then the other one is just by itself.
Then what happened to the x squared?
That factors into those two. It's a difference of 2 squares, like a squared minus b squared. Is that okay? Okay. So now I'm going to do my partial fraction decomposition. So what do I have here? X minus 1 squared, okay. And my next one, x plus 1, okay. And my last one is x minus 1 to the first. So if you have a repeated linear factor, like we do right here, when we do our composition, you need all of its factors. So if it's to the third, you need it to the third, to the second, and to the first. If it was to the 10th, you need it to the 10th, 9th, 8th, 7th, 6th, 5. I mean, you get the idea. It's super annoying. Okay? So we're going to go ahead and clear our fractions, multiplying both sides by that common denominator. So that's going to give me a times x plus 1 plus b times x minus 1 squared plus c times x plus 1 x minus 1. Oops. And all that was still equal to 4x. So that's going to give me ax plus a plus bx squared minus 2bx plus b plus cx squared minus c. So my system is going to be 0a plus b plus c equals 0. I'm going to have a minus 2b plus 0c equals 4. And I'll have a plus b minus c equals 0. Her and Victoria came in late. I didn't get a chance to update.
I'll change it.
Okay. All right, so we go ahead and solve our system. And again, I'm going to use the calculator to do this. If you wanted to do substitution or elimination on this, knock yourself out. I'll pass. Right? Just like one more thing for me to make a dumb mistake on. So there I get A is 2, B is -1, and C is 1. So if I go back to my integral, I have x plus 2 plus 2 over x minus 1 squared plus -1 over x plus 1 plus 1 over x minus 1. Remember, where did the x plus 2 come from?
Wasn't it X?
Oh, was it 1? Yep, thank you. That was the quotient from the polynomial division in the very beginning that we did, but we didn't show. That I said I was going to forget about until I was ready to do the integral. Ready to do the integral, so I brought it back out. Oh dear, Mr. Kulik, I'm going to definitely forget to do that. I know, guys. I know. It's hard. All right, antiderivative time. So x squared plus x. And then how do I do the antiderivative of 2 over x minus 1 squared? Okay. So my u is x minus 1. So that's going to be du is just dx. So I have really 2u to the -2. So that's just going to be, when I do my antiderivative, it's going to be -2u. And then this guy, natural log x plus 1, and the other one, natural log x minus 1. And then my plus c. And I think that's a fine place to stop. If you were so inclined, I guess you could combine those two together. I'll pass, but you write that as natural log x minus 1 over x plus 1. It'd be okay there, I guess. I certainly wouldn't go past that, though. None of that other stuff I want any part of. All right. And I had some other examples on here, but like, I don't think I wanted to do them. So for this set, I just want you to do number 1 and then 7 through 19 odd. So I think both these two assignments are pretty on the light side. Here, as we're getting closer to the end, and I can tell you guys are getting a little less motivated. We're trying to do quality over quantity here and just kind of keep the homework a little bit smaller, especially because some of these things get pretty time consuming pretty quickly. I know, man. We're almost there. We're going to get through this chapter test next week, and we're going to go on spring break, and we'll come back, and we're just going to be doing review stuffs. Okay?
If we,
What day is the check?
if we come back for 5 days.
Probably Thursday next week is be what I would be looking towards.
Which room for a test?
Yeah.
For
We don't have tests.
B? Oh, what are-
Oh, I'm sorry. So Friday next week then. That's tentative, but
Friday.
the goal would be finish chapter 9 on Monday. We'll have a review day Wednesday, and then try the test on Friday.
Yeah, last test was good though.
Everybody okay with tentative plan there?
So are we just gonna like be chilling when we come back from break?
When we come back from spring break, we're probably going, the format of the class will probably be, we're going to do some like multiple choice practice in class, like as some kind of like a group contest. And then I'll give you some free response questions to take home, and we'll have you guys write up your answers on the board, and I'll go through and like tell you how I would score this as an AP grader and where I would have problems giving you points based on what you've written.
Are you an AP grader?
No,
No.
but like
Yeah, you know.
I know how it's done.
Yeah.
But I think that would be really helpful for you guys to see, like, oh, if I didn't do that, or if I forgot this, like, you can't give me the point for this because I didn't put a dx here. Or like, oh, I guess I knew those bounds. I put them in my calculator, but I didn't write it down, and I needed to write like the integral with the bounds on it to get a point here somehow, like stuff like that. So I can just kind of, we can coach you a little bit on the free response about like, if you just write down stuff,
You might get.
there's a lot of sub points, like points inside that are not like directly part of the question, but you can get a point if you realize that, oh, I have to set this derivative equal to 0. Even if you're not sure that that's what you should do, just write it down.
Yeah.
Like
It's something.
it's, like they can only give you points for what's on the paper. But we'll get to that when we get back. But that would be my plan, is to do like a day where we do multiple choice practice and test. I give you a free response question to take home to work on. We come in the next day, everybody writes up their answer. We talk about like, what was good or bad about it or whatever. Maybe I'll have you guys email me a scan of your answer so I can just put them on the projector and go through and grade it in real time.
Yeah.
Or pick out a couple that are like particularly good or bad for whatever reason, or have a good part or bad part to it. But that's probably what the majority of the class is going to look like afterwards. It's just going to be like practicing some skills, and we might add in a couple of other of these miscellaneous like calc 1-2 standard topics that aren't part of the AB. Sprinkle those in here every once in a while, maybe like one a week or something.
Don't we use some like regular calc 2 topics in AB?
Mm-hmm. Yeah. I short of the sequence and series stuff, I think that most of what we do, or what we'll have done in this class, is your Calc 2 course until you get to the sequence and series pieces, which is probably the last half or third of a standard Calc 2 class. At least that's what I remember. But like we'll talk about improper integrals. That's a good topic to talk about, where you integrate to infinity. It's not hard. You just end up taking limits. We'll do like trigonometric substitutions and just like trigonometric integrations. Those are, again, pretty not too terribly difficult. And then maybe like like integration to find like surface areas, which we've done volumes, but we haven't done surface area. We'll probably do that, but those would be the only other topics that I'd want to do. I don't want to go in. I don't want to do anything with sequence and series stuff. It's just too much background. But that's basically what I would do with the last month here of class.
How's your thesis going?
It's on pause.
It is.
Yeah, I just haven't any time to work on it. It
Is
happens.
that like your summer project?
Yeah. There's not enough time.